Use an element argument to prove each statement in 7 through 22. Assume that all sets are subsets of a universal set U. For all sets A, B, and C, A minus B union C minus B equals A union C all minus B. Now, when they say use an element argument, what they mean is that we want to start with an element from this first set, and it's going to be an arbitrary element. We don't know what the element is, but we don't need to know what the element is in order to prove that that element must therefore also be in the second set, thereby proving universally that everything in this first set must be in the second set. The other thing we have to show is that everything in the second set must be in the first set. Basically, we want to show that A minus B union C minus B is a subset of A union C all minus B. And we also want to show that the other set, A union C all minus B, is also a subset of A minus B union C minus B. Let's start with proving the first part. Let X be an element of A minus B union C minus B. Now, we don't know what X is. X could be any element from the set, but it won't matter what that element is because we can unpack the definitions here to clarify what we know about X. And in particular, we want to show that X is an element of A union C minus B. What this means is we want to show that X is an element of A union C, and we need to show that X is not an element of B. So let's start by unpacking this definition. Now, when we're unpacking these operations, we should first ask ourselves, which operation do we unpack first? Now, you always want to work from the outside in. You don't want to start with your parentheses. You actually want to start in the reverse order. So if you're thinking about PEMDAS, which is the order of operations, you're supposed to do parentheses first. When you're unpacking these definitions, you want to work in reverse order. So the first thing we're going to unpack is the definition of union here. X is in the union of these two sets, which means that X is either in the first set or X is in the second set. So we say then by definition of union, X is an element of A minus B or X is an element of C minus B. Now we can unpack what set minus means. So then by definition of set minus, X is an element of A and X is not an element of B, or X is an element of C and X is not an element of B. Now we have to be a little careful about this or here because we want to show that we can get the same conclusion here that X is an element of A union C minus B, regardless of whether or not we're in case 1 or case 2 here. Or, keyword or. So at this point, what we're going to do is we're going to break this up into cases, starting with case 1 is that X is an element of A and X is not an element of B. Now, since X is an element of A, then by addition, which is a logical rule of inference, then X is an element of A or X is an element of C. Let's think why this might be true. If X is an element of A, then X is an element of A, which is why that this must be true because X is an element of A here is true. But we need to state that X is an element of A or X is an element of C so that we can use the definition of union. Then by definition of union, X is an element of A union C. So now we have that X is an element of A union C, and we have the fact that X is not an element of B. Since X is an element of A union C and X is not an element of B, then by definition of set minus, X is an element of A union C minus B. And that works for case 1 here. We also need a case 2. So case 1 was X is an element of A and X is not an element of B. Case 2 is going to be the same thing, except X is going to be an element of C here. Now we can actually copy paste case 1 here, but we just have to make one small adjustment. Instead of assuming that X is an element of A and X is not an element of B, we're actually assuming X is an element of C and X is not an element of B. So since X is an element of C now, then by addition, X is an element of A or X is an element of C. This is still true. Instead of adding X is an element of C to X is an element of A, we're actually adding X is an element of A to the fact that X is an element of C. I'm using the word adding very carefully because the logical operation here is technically an OR operation. So then by definition of union, X is an element of A union C. And since X is an element of A union C and X is not an element of B, then by definition of set minus, X is an element of A union C minus B. This is just the proof of the first part. We want to show two parts. And so now we have to prove the second part, which is that A union C minus B is a subset of A minus B union C minus B. So we'll start with the assumption that X is an element of A union C minus B, and the goal is to show that X must be an element of A minus B union C minus B. Now we want to unpack the last operation done in this expression here, which I know that a lot of you will want to start with this union because PEMDAS tells you to start with parentheses, but we actually have to unpack the set minus first. So then by definition of set minus, X is an element of A union C and X is not an element of B. Next, we can unpack what it means for X to be an element of A union C. So by definition of union, X is an element of A or X is an element of C. And X is not an element of B. So either X is an element of A and X is not an element of B, or X is an element of C and X is not an element of B. So the next thing I want to reference is the distributive laws in propositional logic. You may have seen this before, but this is very seldom used in propositional logic, but this is the distributive law. Basically, we can distribute the AND operation inside an OR operation and just basically separate these two expressions with one OR operation. Now, the distributive law basically says that we can distribute this P and to both the Q and the R to get P and Q or P and R. But here we have X is an element of A or X is an element of C. That's going to be our Q or R here. And X is not an element of B. Okay. So this means then that X is an element of A and X is not an element of B, or X is an element of C and X is not an element of B. But this first part just means, by definition of set minus, X is an element of A minus B, or X is an element of C minus B. And now we can use the union to replace this logical OR operation. This means that X is an element of A minus B union C minus B. And this proves the other part of this proof. So again, there were two main parts of this proof that we wanted to show. We proved the first part by breaking this up into two different cases. And we proved the second part by utilizing the distributive laws. Now, I will say these proofs are really messy. You might be asking yourself, do I really need to write all of this? And the answer is yes. Most teachers will expect you to write all of these details. Now, if you watch the previous video, you'll notice I was a bit sloppy with using all the definitions and explaining what rules we're using. But in a formal proof like this, and specifically an element argument, then we have to be very, very, very careful about every rule of inference that we use and every definition that we need. And there are a lot of definitions here. We have unions, subtractions, subsets, set inequality. All of these things have attached to them a logical foundation. And we can use that to our advantage to make these proofs deductive. Anyways, thanks everyone, and I'll see you in the next video.